Hello everyone, in this video we'll be looking at section 8.5 and picking up where we left off with quadratic factors. So when we're trying to decompose a rational function into its partial fractions when we have quadratic factors. Okay? So essentially what happens is we'll have to work a little bit harder. All right, that's basically what those first two bullet points say. Okay, so let's look at our denominator here. It is x squared minus x times x squared plus 4. We can decompose this, or we can factor that first factor. We can factor an x out, so we're left with x minus 1. And then x squared plus 4 is an irreducible quadratic equation. All right, so I can't break it up anymore. So that's going to be our quadratic factor. Okay, so we leave the numerator alone, right? 2x cubed minus 4x minus 8 over top of our now factored x times x minus 1, x squared plus 4, right? Our factored denominator. And now we write what our pieces will look like, right? Or what our partial fractions will look like. So it looks like a over x, because x is one of our factors and it's linear, plus b over x minus 1 because it's a linear factor. But now when we go to this quadratic factor, remember 1 degree less than that would be linear. So I need to have a linear function, in other words, cx plus d over top of that x squared plus 4. All of these are to the first power, all these factors. So that's why I don't have any squareds or anything in our decomposition. Okay, so just like before here, we need to clear out the denominators. So we multiply by our LCD, which is x times x minus 1 times x squared plus 4. And again, I'm not going to write it out, the steps where I multiply it, but we'll talk about what happens. If I multiply the left-hand side by x times x minus 1 times x squared plus 4, I'm left with just the numerator, right? In other words, it clears out the denominator completely. Now if I multiply this first term by the LCD, the x's will cancel, and I'd be left with an x minus 1 factor and an x squared plus 4 factor. If I multiply this second term by our LCD, the x minus 1 would cancel out, so I'm left with x and x squared plus 4. And finally, if I multiply this last factor, I'm left with a cx plus d, and then my x squared plus 4 cancels out, so I'm gonna have to move this over a little bit to fit it all. On that side, I'd be left with an x and an x minus 1. Right? Okay, so first, try to do what we did before, right? Try to pick out values of x that make everything cancel out, but just leave one of our a, b, c, or d alone. So notice if I plug in, say, 0, 0 will clear out this term and this term, but it will leave the a term there, right? So if x equals to 0, then what do we get? We get negative 8 on one side, right? And then I get a times negative 1 and then times 4. All right, so in other words, I get negative 8 is equal to negative 4a, which means that a is equal to positive 2. Okay. Now we also can notice if I look at my equation and I see that I could plug in 1, and this one would go away and this one would go away, and I'd be left with my b. All right, so if x equals to 1, then my left-hand side would be 2 minus 4 minus 8, which would be minus 10. And then the a term would go away. The b term, I'd be left with b times 1 times 5, right? Because 1 squared plus 4 is 5. And then my c, x plus d term would go away as well. So in other words, I get negative 10 equals to 5b, which means that b equals to negative 2. Okay, so now here's where life gets a little bit harder with these quadratics. Now I can't choose anybody, any other x values to find c and d, and I also can't just plug in a and b and some random x value to get c and d, right? Well, I can, but I won't get c and d quickly, right? So what I need to do is do exactly what I just said, plug in a random x value and b and a that we just found, but I need to do that 2 different times. And once I do that 2 different times, I'll have 2 equations that have cx plus d in them, or c and d in them, and then I'll solve the resulting system of equations for c and d, right? So here, what I'm going to do is I'm going to choose 2 x values and use a equals 2 and b equals -2 to produce a system of equations that allow me to solve for c and d, right? So for example here, let's use x equals to -1, right? Because I already used x equals 0 and x equals to 1. What's another really convenient x value? X equals to -1, right? So if x equals to -1 with our a equals to 2 and our b equals to -2, let's see what happens when I plug that in. So on the left-hand side, I get -6, and then a is 2, and if I plug in -1, I get -2. -1 squared is positive plus what? So this is 5. And then b, we said, was -2. X is -1. -1 squared, so that's 5. And then plus, we're plugging in -1 for c, so this looks like c times -1 plus d, and then we're multiplying that times -1, and then -1 minus 1 is -2. So now we need to simplify this. So -6 is equal to -20 plus 10, and then here this is going to be -c, and this is going to be +2. So I need to distribute that +2 to -c and d, right? So this looks like -2c plus 2d. So I get -10 here, and then if I add that to the other side, I get +4 is equal to -2c plus 2d. So in other words, I get, if I divide the whole equation by 2, 2 is equal to -c plus d, right? So that's my first equation that will allow me, and I'm actually going to move it up a little bit to give us a little bit more room, that will allow me to that we're going to use to solve for c and d. So we got to do that again, right? We'll do it for a different x value. So how about x equals to +2? Right, so scrolling back up to our equation, let's see what we get. If I plug in, so if x equals to +2, again with our a equals to 2 that we already know, and our b equals to -2, what do we get? We get, plugging into the left-hand side of that equation, I get 0. And then a is 2. If x is 2, then x minus 1 is 1. 2 squared is 4, plus 4 is 8, plus b, which we know is -2. X, which we said is 2 here, and then 8. And then plus, and now we get c times 2 plus d, and then multiplied times 2, and then 2 minus 1, which is 1. So 0 is equal to 16 minus 32, and then plus this here is 2c, right? And this here is just 2. So if I distribute the 2 to both 2c and d, I would get 4c plus 2d. right? So this is going to be negative 16. So I add it to the other side, I get positive 16 is equal to 4c plus 2d. And if I divide everything by 2, I end up getting 8 is equal to 2c plus d. So again, that's my second equation. A second equation for my system of equations that I will use to solve for C and D. All right. So we have the system of equations, which is negative C plus D equals to 2, and 2C plus D equals to 8. Right? This is a nice system of equations. I'll call this equation 1 and this equation 2. So now we got to think back to how we solve system of equations, right? We can either solve one equation for one of the variables and then substitute it into the other, or we can conveniently add and subtract equations. So notice that D has this is just 1D in both equations. So if I subtract these two equations, those D's will cancel out. So let's subtract 1 minus 2. Another equation 1 minus equation 2. If I do that, what do I get? I get negative C minus 2C. In other words, minus 3C. D minus D, so those cancel out. And then I would get 2 minus 8, which would be minus 6. So that would give me that C is equal to positive 2. And let's use a different color here. So we used orange, so use red for C equals to 2. And then now we can plug C equals to 2 into either equation. So let's just plug it into equation 1. So I get negative 2 plus D equals to 2. In other words, that means D equals to 0. Let's use blue here. So finally, we found all of our guys, right? So what was our original equation? Here it is, right? So let's copy this here. What is our A? Our A we found to be 2. What is our B? Our B we found to be negative 2. Cx plus D. C is negative, or C is 2 and D is 0, so this just looks like 2x. Whoops, I should have gotten D is equal to 4, not D is equal to 0. You guys are probably all yelling at me, right? If I add 2 to both sides, this is D is equal to 4. Right? So this one should be 2x plus 4. Right? So if I want to integrate both sides, what am I left with? My new integral, instead of integrating this really hard guy from the very beginning, right? Now I can integrate it, and it looks like the integral of 2 over x minus 2 over x minus 1 plus 2x plus 4 over x squared plus 4 dx. So this guy is just going to be a simple 2 ln of u. This one's going to be minus 2 ln of x minus 1 with the u substitution. And in order to solve this one right here, this is just kind of like section 8.1 where we've got to figure out a good strategy. And actually breaking up the numerator is going to be the best way to do that. Right? So I'm going to rewrite this as 2 over x minus 2 over x minus, over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4 dx. And then now this guy is going to be a tangent inverse. This guy is going to be a u sub. This guy is going to be a u sub. And 2 ln of x is going to be easy. All right? So it ends up being the final answer. I won't waste our time with going through all of those integrals for every piece because that's more like a section 8.1 problem. But our final answer ends up being 2 ln of the absolute value of x minus 2 ln of the absolute value of x minus 1. When I do u substitution here, I end up with 2 ln of x squared plus 4. I can get rid of the absolute values in that case because x squared plus 4 is always positive. And then if I look at that last one, the 4 hangs out for the right, and then it's exactly an arctangent that looks like 1/2 tangent inverse of x over 4, or sorry, x over 2. And then now 4 times 1/2 is going to be 2, so I can actually simplify that. So it's 2, and then I get my tangent inverse of x over 2 plus c. So the beef of this problem is to obviously decompose it into the partial fractions, but unfortunately there's still more work to be done, which is solving these integrals like we know how to do from previous sections. Okay, so examples 1, 2, and 3, the ones we've looked at so far, we had in a basic equation that we could just substitute values in x in because we had linear factors, right? In the case, so like starting right here, how were we able to get a equals 2 and b equals -2? Well, we had linear factors in our equation. So since we had linear factors in this equation up here, we were able to just plug in x values and be able to solve for a and b. If I have no linear equations, though, I can't do that. And so now we'll see what will happen if I have no linear factors. In other words, I just have repeated quadratic factors. Okay, so repeated quadratic factors, x plus 2 quantity squared does not, is irreducible, right? So this really is just x squared plus 2 quantity squared. It's factored already. So this looks like 8x cubed plus 13x over x squared plus 2 quantity squared. And now we have this x squared plus 2, which is a quadratic, so it needs an ax plus b over it to the first power, and then it also needs a cx plus d over it to the second power, right? Okay, so now as before, we clear out the denominators, so we're going to multiply by our LCD, which is just x squared plus 2 quantity squared. If we do that, the left-hand side, we're just left with the numerator, x cubed plus 13x, and then I'm left with ax plus b, and one of the factors of x squared plus 2 gets left over. And then if I multiply the second term here by x squared plus 2 quantity squared, the denominators cancel, so I'm left with cx plus d. Okay, so normally what we would have done in this situation was start plugging in x values, but that's not what we're going to do here. What we're going to do here is try to simplify everything first. So we need to distribute, or we need to FOIL that guy right there. So I get 8x cubed plus 13x is equal to ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. Okay, so now what I'm going to do is going to seem a little bit odd, but you'll see why I'm doing it. So I'm going to rewrite the left-hand side in descending powers of x's with 0 place values for, like, say, x squared in the constant term, right? So this is going to look like 8x cubed plus 0x squared plus 13x plus 0, right? So everybody's accounted for. Now I'm going to do the same thing on the right-hand side. I'm going to combine all of my like terms with x squareds and x cubes and x's and constants. All right, so x cubed is just ax cubed. And now x squared is just going to be plus bx squared. But now if you notice, 2ax and cx are both my x terms. So if I factored out the x there, I'd be left with 2a plus c times x, right? If I combine my linear terms. Now I see 2b and d, and I don't necessarily have to put these parentheses around it, but I just kind of like to, and you'll see why. So here I get 2b plus d create my constant term. All right, and again, if you don't believe me, distribute the x to both terms there, and I'm back up to the previous line. So why is this helpful? Why did I do this? Well, now what we can do is we can equate the coefficients of each power of x. Right? Because here on this left-hand side, if I have 8x cubed on this side and I have a nice equal sign right here, well, that means that whatever the coefficient for x cubed is on the right-hand side has to be equal to the same thing. So in other words, a is equal to 8. And 0 has to be equal to the coefficient of x squared, which is b. And 13 has to be equal to the coefficient of x, which is 2a plus c. And 0 has to be equal to the coefficient of the constant term, which is 2b plus d. So I get a whole system of equations here. I get from my x cubed, I need to get that 8 is equal to a. Cool. And that gives me an answer for what a is, which is one of the things we wanted, right? We want to figure out all of our variables, all a, b, c, and d. So then I get 0 is equal to b from my x squared terms. Let's try that again. 0 is equal to b. And then I get 13 is equal to 2a plus c. So we're like, oh, crap, how do we get c? Well, we know what a is, right? A is 8. So I get 13 equals to 2 times a, which is 8, plus c. So I get 13 is equal to 16 plus c. In other words, negative 3 is equal to c. All right, and that's what I get from my, let's see, did I have colors? No, I didn't have colors, this one. And then from my last one here, I get 2b, whoops, try that again. On my left-hand side, I get 0 is equal to 2b plus d, right? So how are we going to find d? Well, we know what b is, right? b is equal to 0. So that means that 0 is equal to d. And that's where I get my other term. So I guess maybe what I should do here, the purple should be that equation, and the green should be this equation, right? Okay, so now I know everybody, right? So we go back up to this term here. Whoops, not cut. We go up to here, we copy. We paste. I don't really want an image. Sorry, technical difficulties. Copy. We just want a regular paste. Okay. And now we know everybody, right? We know a, b, c, and d. So ax plus b is now 8x, right? Because b is 0. And then cx plus d is minus 3x. All right? So if I wanted to find the integral of our original function, which was 8x cubed plus 13x over x squared plus 2 quantity squared, well, that would be the same as finding the integral of 8x over x squared plus 2 plus the integral, or I guess we could say minus 3x over x squared plus 2 dx, right? This one, it's going to be a u sub. Why? Because my inner function will be x squared plus 2. The derivative of x squared is 2x, which looks a lot like our numerator. And then here, is also going to be a u sub with u equals x squared plus 2, right? I will, because when I take the derivative of my inner function, I will get 2x, which looks a lot like the numerator, right? And so I won't waste our time with those, well, I won't waste our time with those u substitutions because, again, that's like more like section 8.1. But if you were to do those u substitutions correctly, you would get the answer of 4 ln the absolute value of x squared plus 2, but x squared plus 2 is always positive, so I can get rid of those absolute value signs, and then plus 3 over 2, or in other words, 3 halves times x squared plus 2, and then plus c. So this would be the answer if you did both of those u substitutions correctly. Okay, so just to rehash, when integrating irrational functions, keep in mind that if I have an improper rational function, right, in other words, if the numerator degree is bigger than the denominator degree, then what do? I must use long division first. And then I will get some rational equation here that I can use the tricks that we just learned on, right? But I have to divide out first in order to do this partial fraction decomposition. Okay, so guidelines for solving those basic equations, right? In other words, how do I find my a, b, c, d, and so on? If it's just linear factors, then I substitute the roots of the distinct linear factors into the basic equations. In other words, choose those x values that make some of my factors go away, go to 0. If I have repeated linear factors, that's where I have to find a couple of them through however many I can through substituting x values, and then I have to find a system of equations, right? We did one example like that. If I have quadratic factors, then I will have to expand. This is just like the previous problem that we did there. What did we do? We expanded everybody, right? And this part right here that I'm starring, we expanded everything. And then we were able to equate coefficients of powers on each side of the equation, right? And that gave us a system of equations that was really easy to solve for A, B, C, and D in our case, right? All right, thank you.